first speaker is Professor Hugh Durrant-Whyte. Hugh is the Chief Scientist of New South Wales. Previously, he was the Chief Scientific Advisor to the UK and the Founding Director of the Australian Centre for Field Robotics at the University of Sydney. He has here that he's a world authority on machine learning and robotics and their application in areas. Anyway, it's with much pleasure that I introduce you.
Pleasure to be here and to talk about uncertainty in making decisions around natural resources. Natural resources is a really interesting area because when it comes to data, I think it is sine qua non when it comes to lack of data, lack of models, high levels of risk, and what we call opting decisions. That is, you genuinely make a decision and don't really know the outcome of that decision for years, sometimes decades into the future. And allied to that is this whole problem, I guess, of managing that very high level of uncertainty, not just uncertainty, even ambiguity, the fact that many different people interpret the same data and the same models in very different ways, and also the fact that typically in natural resources, you need to communicate that uncertainty, and it's at the heart of what we do. So you need to not just work with it, but communicate it to the community that it impacts, and of course to the decision makers, in my case, the politicians who make decisions with that sort of information. So natural resources really is an area that really captures the really intrinsic complexity of uncertainty in decision making in so many ways. I actually now have two roles. I am the Chief Scientist of New South Wales, and I am also the Commissioner for Natural Resources. In my Chief Scientist role, we provide evidence-based advice right across government in a whole range of different areas, and I will give some examples of this in a few minutes. But typically they are indeed in areas which are extremely controversial. The more controversial the better, mining in the catchment, coal seam gas and things like that, and that genuinely have this whole issue about uncertainty across the whole space of both data and models. And yet in the end, we have to provide advice that genuinely makes the right kind of decision by government, marrying all these different things together. So communication is very important. The Natural Resources Commission has a subtly but importantly different role. It is a statutory body, and it is genuinely there to provide independent and often challenging advice to the government around key things like, for example, forests. A big issue at the moment with the impact of fires that we had earlier in the year, and also areas like water, and you'll hear from Jim Bentley later. But water is a particularly contentious issue in Australia. So the typical roles is really to provide, again, evidence-based advice, to balance competing interests, certainly in my Chief Scientist role, commercial, societal, and environmental, and really to grapple with, I think, what are arguably some of the more complex problems that we have. As I said, mining in the catchment, bottled water, and as I'll talk about in a minute, managing the wild horses in the Kosciuszko. None of these jobs are easy, and everyone has very polarized opinions. One of the things we've been doing in my office over a year or two now is really trying to build a much more principled approach to providing advice and providing advice about decision making and understanding uncertainty. And also, we've been very, very conscious of the need to communicate to decision makers what that uncertainty actually means. And in doing that, we think about actually two subtly different things. We think about different types of uncertainty, and I'm going to talk about that in a minute. And we also talk about understanding the impacts of those uncertainties on the decision making process. So very briefly, we have a kind of standing process now where when we look at these problems, we think about actually four levels of uncertainty and how to explain these. I mean, at the very smallest end, we have things like measurement uncertainty, measurement noise indeed. And it's kind of the easiest thing to explain, that there is some variability in the data, you would expect that, or sometimes that sensor may need calibrating or these sorts of things. And genuinely, we know how to handle that kind of problem. But even so, at that level, we often find our community not really understanding what an error in a measurement actually means. Not that it's wrong, but basically it's an expected part of the physics of what's happening. The second level of uncertainty that we often talk about is estimation error. That is where we go from data to actually coming up with some parametric quantity. and that parametric quantity is often part of the decision-making process. And, you know, genuinely, again, that's a well understood problem. We can quantify that. We can provide some measure of that level of uncertainty. And again, for most significant decision makers, I think they understand that. The other two levels of uncertainty, though, are that much more complex, and we find a great deal of problems really getting these ideas over. The first one is model uncertainty. That is, there's often, firstly, not known really with any precision what the model is, and you have to think of something like a groundwater aquifer, or indeed the model is just not really quantifiable at all. So what is the impact, for example, of chopping down a forest today? What will be the impact on wildlife 20 years from now? People just don't have good models for that. And how do we account for that in the uncertainty when we offer a decision maker the options of cutting down or not cutting down that forest or whatever else it may be? And you often see this also in areas like in chemicals and a whole range of things where that model piece is not known. Having said that, at least it's graspable. So it's possible to put bounds on what we do know and what we do not know, and try and make the decision making that we actually undertake robust to those sorts of processes. And the fourth area are what I think of as acts of God, where we genuinely just don't have any examples of it happening before, but it might happen. And a good example I'd like to come up with, I guess, is the height of dams. You know, there's lots of pieces in the newspaper, or was certainly a year ago, about the fact that at the same time that we were having climate change issues in the sense of wondering whether we had any water that was going into the Warragamba Dam, we were also looking at the possibility of building an extra 14 meters on top of the dam. Because, you know, although we have never had a flood like that, it is quite conceivable that we could have a flood. And indeed, when you look at climate change models, it may well be that events like that happen. But we have to sort of guard against the extremes in that case without, if you like, being completely silly about it. You know, if we took everything as an act of God, then frankly, we wouldn't do anything, and we wouldn't balance the decisions that genuinely need to be made. So in all the decisions and all the kinds of reports and advice we give, we think about these four levels of uncertainty and how they actually might come together in the advice that we give. So the second part of the decision-making and managing uncertainty piece is really the way that we actually use that information to make decisions. And, you know, there is a kind of process I think one goes through when you have these sorts of things. You have to get a really good grip on the problem. So, you know, if it's about contamination, or it's about forestry, or lack of resources, or these sorts of things, you genuinely need to have some bounds on the problem and understand what questions it is that you're actually trying to ask. Because if you try and answer general questions about these sorts of areas, you will never get you will never have enough data and never really be in a position to make a good decision. The second thing is really the role of sensing and modeling, and kind of, there's always this payoff, you know, if you had lots and lots of sensors and you could take almost infinite numbers of measurements, you really probably wouldn't need a model. Conversely, if you've got really, really good modeling capabilities, then you need less sensing. And it's an issue of how you mix those two things together to genuinely coming up with a plausible understanding of the problem and a way of taking that forward. And we see this in a lot of different areas. Often you're very limited in terms of data. I think of the Murray-Darling Basin, really not many measurements, lots of models. We don't really know a priori what we might happen. And yet at that point, we still got to make decisions around our allocation to wildlife, to the ecology system, as well as to irrigators and commercial actors and so on, that all need to share that. So what is the right decision? And how do those models and what sensing should we use to make that decision making, that modeling, robust to the sorts of decisions that the decision makers really need to make? And the other piece in here is about, you know, data and models that are really fit for purpose. It was one thing that came across my desk 3 or 4 months ago around, again, water modeling. I hate to say that water keeps on coming up, and I'm pleased you're going to have Jim coming after me. But the real issue around, do we actually have the data we need to make decisions about water allocation? And more than that, do we have the right models, given that most of our models were developed in a time before significant climate change? And if you look at the rainfall patterns we have now, they're arguably significantly different than what they are in the past. We probably need to be starting to build different models, new models with new data to come up with, if you like, an ability to predict far enough in the future that we make sensible decisions about water resilience and water usage and so on. So these are very complex problems, and a handle and a proper approach to understanding and managing the uncertainty in that process is absolutely critical. And then I come to often what I find is probably the most challenging problem. I almost like to draw a distinction between uncertainty, that is, I can put some probabilistic model on something, and genuine ambiguity, in the sense that I really do not know whether it's A or B, and I could not even put a probability on it. Often you end up with situations in which you have very complex models and you have very little data, and it's quite ambiguous what the outcome might be. And there are certainly ways of addressing that in probabilistic frameworks, looking at probabilities over models and many other approaches. And again, this is a foundational piece of work for what will probably happen in the ARC Centre that Sally and colleagues run. But you genuinely need to grapple with these very, not just uncertain, but genuinely ambiguous modelling problems, and how you actually use information to get hold of those. And then there's this final piece about, well, not final, second to last, robustness. So, in the end, with all of these models, with all these probabilities, somebody needs to make a decision and stand by it. And, I think our role increasingly is to try and explain where the uncertainty sits, so that decision makers at least are aware, but at the same time are not so over conservative that they never do anything. Because that's always a problem. I will never let this chemical be used in case A, B, C, D, E, F, and G all happen at the same time. And so you've got to be careful about the way that you not just communicate that, but ensure that the decision makers understand the impact or otherwise of what they're doing. And then the very final thing that I think often is not mentioned in conferences like this, but I found one of the most challenging things in everything we do, which is engaging the community. We go out there with lots of things and we have all these probabilistic models and we think we can put values on things, but we go out to the people whose aquifer they actually use, or the environment in which these people actually live, or indeed the commercial user of these resources, and we have to say to them, I'm afraid you can or you cannot do this because the evidence says that. And I will say it's very hard to get an understanding of evidence and uncertainty in that evidence across to a community who have inbuilt reasons to believe that it's wrong. Some days they call it fake news, but I just say it's an inability to explain that uncertainty and that ambiguity. And I find that one of the most challenging roles that people in our community have to put together. So I wanted to just briefly talk. I'm trying to figure out if I started at, I've got 4 minutes, I reckon. Just a couple of projects that we have. In my offices, I have about 12, a dozen different projects at any one time underway in the Chief Scientist's office. And we have about 20, I think, or something like that at the moment in the Natural Resources Commission. So we really do manage a lot of these different programs in the state government. And I just wanted to give you an idea of some of the things that we do. And I thought I'd start with one which was an intriguing one for me around bottled water. In the Tweed area in northern New South Wales, there are aquifers, and there is a bottled water industry, and they extract they extract water from these aquifers. And of course, they then go and sell that in bottles as a bottled water thing. And you may object to a number of different things in that. You may object to the fact they're using plastic bottles, that they're driving trucks around, or whatever else it may be. But also you might object to the fact that they're using scarce water that could be used for agriculture. So we had a project that looked at this. It was interesting, that actually in this case, there's actually quite a lot of data, and you could come up with a fairly irrefutable decision that actually the bottled water users industry were probably not really using much of what was in the aquifer. And yet, the perception in the community was that they very much were, because what they saw on the surface was surface water drying out. And of course, surface water and aquifers are correlated, although of course we've been in a fairly extreme drought situation, and yet no amount of evidence in some sense, no amount of modeling, measurement, uncertainty and so on, really could try and get the right case across. And so it was a challenging project, not because of the measurement uncertainty, but actually, if you like, the kind of modeling uncertainty and the fact that the community latched onto that and had a different decision about the way that things should happen. The other one, which I have struggled with and people lament with me about, is what to do about the wild horses in the Kosciuszko National Park. So I'm a part of the committee in that. I can't say too much because it's currently sitting at the moment, but I will say, and this is in the public area, that you know, we take measurements of how many horses we think are in the area. That's done, in fact, by someone in a helicopter flying over and essentially counting them. We do that about once every 4 or 5 years. And this time round, the number of horses in the park was estimated to have risen from about 7,000 or 8,000 to 25,000. And you can imagine that the community weren't too happy about that because, well, different parts of the community. Firstly, the ecology side of it, because horses, without question, damage the park, certainly if there's too many of them. And of course, the people who are, you know, who are very pro-Brumby, on the other side, didn't want to see such a large count because it meant that in the end, something had to be done about it. And so there's a kind of data uncertainty, but also in truth, there's a model uncertainty as well. There's a model in terms of the way we gathered that data. There's a model in terms of the way that those horses damage the environment. And then there is a really tricky decision, an awfully tricky decision, that despite all of that uncertainty, how would you go ahead and manage the horses so that indeed the competing interests of the indigenous population, the ecology and wildlife of the area, the people who, who want brumbies to be there for historical reasons and many others, how are all those interests put together? And the uncertainty and ambiguity in that decision making, if I removed half those horses, what would be the impact on the environment 3, 4, 5 years, a decade from now? And how do I communicate that to the community is a very, very big and complex problem. So I could go on to many others, PFAS, pollution, forests and koalas, which has been in the news recently, whole ranges of these different things. But I want to leave you with the following thing. I want to leave you with the fact that this understanding of uncertainty, this understanding of how to manage uncertainty, this embracement in some sense of uncertainty is going to be key to any of these sorts of decisions going forwards. And we need to be, you know, we need to be in a position where we have new methods, new techniques for not just managing that uncertainty, but using it and exploiting it in effect to provide the best advice and to get ministers and others to make the best decisions with that information. So this conference and the centre, I think, are exactly on the right track and critical to all our natural environment futures. Thank you very much.